Every time you open a website, about 15 different networking events happen in under 200 milliseconds. Most developers know maybe 3 of them. That's not a criticism. Most of these events happen invisibly, automatically, deep in the system, but that's exactly the problem. Because networking is not optional. Whether you write backend code, do DevOps, or deploy anything at all, sooner or later, your code runs over a network. And sooner or later, something breaks. And when it does, you need to know where to look. So let's start from the beginning. Not with theory, with a story. Imagine you just built your own app. A small online tool. Nothing big. To make this concrete, let's use a real example. PaperOffice AI, a tech company I have been working on for over 20 years. PaperOffice AI is a document AI platform that processes, understands, and routes documents through APIs, OCR, LLMs, and automated workflows. My name is Irina, and if you watch this video to the end, you'll learn how to scale from zero to production, avoid the infrastructure traps most developers fall into, and build systems that actually survive real-world traffic.
And we'll use that growing system as our story, from one server to real infrastructure.
You rent a server, install everything, start the app, and then you ask yourself the simplest question in the world. How is anyone supposed to find this? Your server is sitting in a data center somewhere. No name, no sign, nothing. That's the first problem, addressing. Every device on the internet gets an IP address, a number like 142.250.185.46. That's the real address of your server, like a house number. Without it, nobody finds you. The app runs. Users are coming in. All good, until the first internal service appears. Then you realize you need a database and an admin panel, and maybe a small API service. You install everything on the same server, same IP address. When a request arrives, which of the 3 apps should receive it? Ports. A port is like a door number in a building. The building has one address, the IP, but inside there are many doors, the ports. The web app listens on port 443, the standard for HTTPS. The database might listen on port 3306, 5432, or another internal port, depending on the system. The admin panel on port 8080. When a request comes in, the port decides which app is responsible. The 3000 is the port. Your local dev server runs on port 3000. It took me months to really understand this, and yet it's so simple once you think it through. One address, many doors. And the moment your app grows, those doors become security decisions. And this works until success creates the next problem. More users, more data, more responsibility. And then you notice everything runs on one server. Database, backend, front end, all together, open, connected to each other. An attacker would only need to break in once, and they'd have access to everything. It's like living in your apartment, working there, sleeping there, keeping your valuables there, and never locking the front door. The solution? Split the network into subnets. Public areas for what actually needs to be reachable from the internet. Private areas for backend and logic. Strictly protected areas for data. Each area has its own IP range, its own rules. If the front end and database are in different areas, how do they talk to each other? That's where routing comes in. A router is like a postman who knows the routes. He doesn't know the destination personally, but he knows the direction. Now the rooms are separated. But separated rooms are not secure if every door stays open. The network is split. Good work. But here comes the next trap. Just because areas were created doesn't mean they're secure. Imagine your office has different departments: accounting, engineering, management. Each has its own hallway. But all the doors are open. Anyone can walk anywhere. That changes nothing. That's why we need firewalls. A firewall is not a virus scanner. That's a different topic. A firewall is a rule book. Incoming traffic is allowed only on port 443. Everything else from the outside is blocked. The database can communicate only with the backend. Direct database access from the internet is not allowed. And the key thing, you build firewalls in layers. One at the network edge, one on every server. If one layer fails, the next one catches it. This principle is called defense in depth. Now, the backend servers have private IP addresses, not reachable from outside. Perfect dash until they need to reach out themselves. But they sometimes need to reach the internet themselves. Software updates, external APIs, downloading packages, and the public internet cannot route back to private IPs like 10.0.0.5 directly. That address only makes sense inside your private network. How do private servers reach the internet without exposing their private IP addresses directly? The solution: NAT-network address translation. Imagine a company phone system. Every employee has an internal extension, but outbound calls go through the main company number. The other side sees the main number, not the internal extension. NAT works similarly. Private servers send requests through a NAT gateway. The gateway translates the private source address into its public address for that connection. When the response comes back, the gateway knows which private server should receive it. Private inward, reachable outward. And now the infrastructure starts to look like cloud networking before we even call it cloud. At some point, the system grows again. Managing physical servers yourself stops making sense, so you move to the cloud. And here's something that surprises a lot of people. The cloud doesn't reinvent networks. It wraps the same concepts in managed services with new names. VPC Subnet Route Table Security Group, NAT Gateway. If you know the fundamentals, you look at Cloud Docs and think, I know this, different name. If you know the cloud but not the fundamentals, you'll hit a wall eventually. And then the next problem appears. The application itself starts splitting into pieces. PaperOffice AI is no longer one big monolith. The system starts splitting into smaller services. OCR becomes one service. Search becomes another. AI processing becomes another. Docker puts each service into its own container. Same code, same environment, same behavior, on a laptop, on a test server, or in production. But now there is a new problem. The OCR service runs inside the container on port 8001. How does the outside world reach it? Simple. We map the port. Host port 9001 goes to container port 8001. And yes, that is basically NAT again. Address translation just one level higher. But when containers run on different servers, Docker goes further. It creates overlay networks. A container on server capital A can talk to a container on server capital B as if both were in the same room, and that is where services become movable, scalable, and flexible. Now the system starts behaving less like a machine and more like a living organism. Dozens of containers, hundreds of containers. Kubernetes manages them automatically, but this creates a new and very dangerous problem. Kubernetes can stop, restart, or move a pod at any time. And every time this happens, the pod may receive a new IP address. So, if the front end talks directly to the IP address of a backend pod, and that backend pod restarts, the connection breaks. Kubernetes solves this with services. A service is a stable address in front of changing pods. No matter how often the pod behind it dies, restarts, or is recreated, the address stays the same. The front end connects to the service. The service knows where a healthy pod is, and the user notices none of it. But then there is another question. How does external traffic get into the cluster? For many years, the answer was ingress. Ingress is an intelligent gateway at the edge of the Kubernetes cluster. For example, traffic for PaperOffice AI/API/OCR can go to the OCR service. Traffic for PaperOffice AI/API/Docs can go to the Docs service. And traffic for PaperOffice AI can go to the web app. One address on the outside, many services behind it. But modern Kubernetes is now moving one step further. Ingress was simple. Gateway API is more structured. The platform team can own the gateway, and the application teams can attach their own routes to their own services. Same idea, cleaner ownership. And once you understand those fundamentals, infrastructure stops feeling like a black box. You no longer guess where the problem is. You know where to look. That is the difference between using infrastructure and understanding it. If this helped you see the internet more clearly, subscribe to the channel. In the next video, we go one step deeper. We will look at what happens after Kubernetes. Gateway API, Zero Trust, Observability, HTTP3, and eBPF. Modern infrastructure is not just about connecting services anymore. It is about ownership, security, visibility, and control. Subscribe now, and I will see you in the next one.